Let's look at other classification of the grammar. Based on the way the productions are defined, we can even classify the grammars into two types. Left recursive grammar and right recursive grammar. What do we mean by left recursive grammar? If at all you take the productions in the grammar, if they are defined like this, A to A alpha or beta, that means the non-terminal on the left hand side is same as the leftmost on the right hand side. If these two are same, it's called left recursive grammar. Whereas if the productions are of the form A to alpha A or beta, that means non-terminal on the left hand side is same as rightmost on the right hand side, then it is called right recursive grammar. This is left recursive grammar, that is right recursive grammar. Let us try to understand what are the problems with such grammars. If you look, consider alpha beta to be some terminal symbols. The language defined by this grammar can be something like A to beta alpha star, whereas the language defined by this grammar can be alpha star beta. So if I take a string something like beta alpha 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 as my input string here, how do I derive this input string? By using this grammar. Start with A. A can be A alpha, A can be A alpha, A can be A alpha and then beta. When the grammar is left recursive, when you construct the parse tree, the tree grows towards left, that is left recursive. So here if you assume this A as a function, what is happening? Initial A is expanded with A alpha. Remember, in order to derive the string, always any parser reads the input string symbol by symbol from left to right. That means initially it will read beta, it will wait until beta is derived, then it will go with the next symbol, that is alpha. Once this alpha is derived, then it goes to next symbol and so on. Always traditional reading is symbol by symbol from left to right. But if you look at this derivation process, when exactly it will get beta? As a last symbol. So if you consider each A to be a function, a recursive function, A calls to itself without recognizing or deriving any input string. Hence there is a danger of going into infinite loop. Since call to itself, this depends on the length of the string. Hence there is a danger of going into infinite loop. That's why certain parsers actually does not accept this left recursion. Especially the top-down parsers actually does not accept this left recursion. Now before going further into left recursion, let us try to understand whether this problem is there with the right recursive grammars also. So here once again, if you take a string something like alpha 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 beta, a string out of this, how do we derive? First one is alpha, so A is replaced by alpha A. So the part of the input string is already recognized. First alpha is recognized. So once again replace A by alpha A. Second alpha is also derived. Replace A by alpha A. Third one is also derived. Hence finally replace this with beta. So at every step, since partially input string is recognized, it knows very clearly when to stop. Whereas here, since it is looping at every step, it may not be knowing when exactly it has to stop. Hence there is a danger of going into infinite loop. Whereas in right recursive grammars, there is no such danger. So given a grammar, left recursion makes the, if you use a left recursive grammar for the construction of a parser, generally parser your top-down parser uses only leftmost derivation, there is a danger of going into infinite loop. Since there is a danger of going into infinite loop if you use a left recursion, some parsers does not accept. In that case, what is the solution? So when there is a left recursion, how do we convert or how do we eliminate left recursion from the given grammar? So if there is a left recursive grammar, how do we eliminate left recursion? Since it is not accepted by few parsers, if at all we want to eliminate left recursion, actually there is an equivalent grammar with, you can always rewrite the grammar without left recursion like this. Whenever there is a left recursion like this, to eliminate the left recursion, you rewrite the grammar like this: beta a dash to alpha a dash or epsilon. Remember, you can consider this as a formula. Whenever there is a left recursion like this, the equivalent without left recursion can be given like this. So before using this formula, let us try to understand how do we get this equivalent without left recursion. So for that, let me take an example. Suppose if I take a expression grammar e to e plus t r t, t to t star f r f, f to id. I have a grammar in context-free grammar. Here I want to convert this grammar into extended Backus-Naur form, EBNF notation. In EBNF notation, the notation what we use is, whenever you have some string within the curly braces, the meaning of that is 0 or more occurrences of the string str. It is 0 or more occurrences of the string. So let us try to rewrite the given grammar into EBNF notation. So in order to convert this CFG into EBNF notation, if I want to introduce this, let's see how we do. Suppose if you take the first production e to e plus t or t does what? E in simple can be t, or e can be e plus t, that means it can be t plus t, or I can once again expand this with e plus t, that means it can be t plus t plus t, or in simple t plus t any number of times. So it defines t followed by plus t any number of times. If it is 0 times, it is only t, 1 or more times means t plus t and so on. So I'll rewrite the first production as in EBNF, this CFG into EBNF notation like this. E can be t plus t. That takes care of defining 1t or 2t's or 3t's or 4t's, like t plus t, t plus t, t plus t and so on. Because the meaning of this is 0 or more occurrences of plus t. Similarly, if I take the second production t to t star f or f, it can be 1f or f star f or f star f and so on. So in simple, I can say t can be f star f, whereas f can be id. So this is the EBNF notation. The given grammar is in CFG. I have converted that into EBNF. To eliminate the left recursion, remember, I am trying to do this. I have a given grammar wherein there is a left recursion. How do you say there is a left recursion? Whenever the leftmost on the right hand side and the non-terminal on the left hand side are same, we call it as a left recursion. So in order to convert or eliminate this left recursion, what I did, I have taken the CFG and converted that into EBNF. Look at this, do you have that left recursion? No. So to eliminate the left recursion, I have converted that into EBNF form. Yes, now if you look at this, there is no left recursion, but this is not the accepted solution, because I want even the solution also to be in context-free grammar only. So let us convert this EBNF into context-free. How do we convert? Wherever you have introduced a new notation, define that with a non-terminal. So I'll rewrite the grammar like this. E can be T E dash. Let this part be some E dash. Now if E dash is meant for defining this, what exactly is the meaning of whatever you have within the curly braces? 0 or more occurrences of plus T. So I'll say 0 occurrence or 1 occurrence. 1 or more occurrences means let it be recursive. This takes care of defining any number of occurrences. Similarly, for T, F, for this T dash, where T dash can be 0 occurrence or 1 occurrence of this or 1 or more occurrences, and then F to ID. Look at this resulting grammar. Do you have any left recursion? Check out each and every production. These two are not same, hence there is no left recursion. In the given grammar, there is a left recursion at two places, E, E, T, T. Whereas in the resulting grammar, now there is no left recursion. This is how we can eliminate the left recursion. Now you compare this grammar with the original grammar. Whenever you have E to E plus T, okay, then we have to eliminate that. This is the equivalent for this particular grammar without left recursion. So if you compare these two, you will get that formula. So when there is a left recursion, something like A to A alpha or beta, to eliminate the left recursion, rewrite that as A to T is beta A dash, where A dash is what? Is plus T, which is nothing but alpha A dash or epsilon. So that's how we get whenever there is A to A alpha, A to A alpha or beta, it is A to beta A dash to alpha A dash or epsilon. Same thing you will get even if you compare this with this. This is the original grammar with left recursion. When you eliminate the left recursion, the equivalent grammar is this. So once again here also A, so naturally this is also A, this is alpha and this is beta. If you assume this to be A and this is alpha and this is beta, in the equivalent this is A, F is beta and this is A dash, where A dash is what? Epsilon or star F is alpha A dash. A to beta A dash to alpha A dash or epsilon. So that is how we get this formula. So it is better to remember this particular formula. Whenever there is a left recursion, eliminate the left recursion by using this. So this process is very important. Let us take few examples to understand how to eliminate the left recursion. Let us take few examples to understand how to eliminate the left recursion. So what is that we should remember to eliminate the left recursion? Whenever there is a left recursion of the form A to A alpha or beta, rewrite that as A to beta A dash to alpha A dash or epsilon. For example, take this. Eliminate the left recursion in this given grammar. So first check out which particular production has the left recursion. So look at this leftmost on the right hand side and the left hand side non-terminals are not same, so no left recursion. Here there is a left recursion, no left recursion, no left recursion, no left recursion. There is left recursion only at this place. So how do we eliminate? Whenever there is a left recursion, view that particular production as the form A to A alpha and beta. Let this B be alpha and C be beta. So what is the equivalent? The equivalent is given by A to beta A dash, that means B to C B dash, where B dash is what? Alpha A dash, alpha here is B, so B B dash or epsilon. So you can simply replace this with two productions, remaining all productions can be as it is. That is the equivalent grammar without left recursion. Only this you replace by these two, all this can be added as it is. Remember, this left recursion can even be generalized. That means If there is left recursion at more than one place, that means if you have something like a to a alpha 1, a alpha 2 and so on, beta 1, beta 2, beta n. How do we eliminate the left recursion here? When left recursion is there at more than one place also, we can generalize by using the same formula. So take out all the alternative productions which are not starting with the same non-terminal. So write that as a2 beta 1 a dash, beta 2 a dash, beta 3 a dash and so on, where a dash is alpha 1 a dash, alpha 2 a dash and so on, but this last r epsilon is most important. Let's have an example for this. Take this particular example. Look at this example. Eliminate left recursion here. Where do you find left recursion? Here there is no left recursion, here there is no left recursion, here there is no left recursion. Left recursion is only at this place, more than one place. So how do we eliminate? A2, beta 1 a dash, beta 2 a dash. So here this is your beta 1, this is your beta 2, this is your alpha 1 and this is your alpha 2. So rule is what? Beta 1 a dash, that means AB a dash, AC a dash, where a dash is D a dash, E a dash or epsilon. So you can use this generalized rule also in the same manner. Beta 1 a dash, beta 2 a dash, alpha, where a dash is alpha 1 a dash, alpha 2 a dash or epsilon. That is how you can eliminate. Let us take one last example. Look at this. How do we eliminate the left recursion in this grammar? In the first rule, there is no left recursion. These two are not same. Whenever you have a to a only, same non-terminals, then only there is a left recursion. So there is no danger here, but whereas here there is a left recursion. So what is the rule? Once again visualize this as a to a alpha. A, this is your alpha and this is your beta. So rewrite L as a to beta a dash to alpha, here is what? Comma s, L dash or epsilon. Comma is also a terminal here. So comma s is your alpha. So alpha a dash or epsilon. This a dash or L dash, anything can be used. So that is how straight away by using this formula you can always eliminate left recursion. Let's look at one more example. S2 triple S are A. Is there any left recursion? Yes, because these two non-terminals are same, there is a left recursion. How do you eliminate? Use the same formula. Whenever there is a to a alpha or beta, rewrite it as a to beta a dash to alpha a dash or epsilon. So if I use the same thing, a, this is alpha and this is beta. So I will rewrite as a to beta a dash to alpha a dash or epsilon. Look at this formula. This formula actually eliminates immediate left recursion. Okay, even take one more example. Look at this. How do you eliminate the left recursion in this grammar? Same formula. This is your alpha and this is your beta. So S2 beta a dash to alpha a dash or epsilon. Now let me take a different example. Look at this. Do you have a left recursion in this example? There is a left recursion. Is left recursion is there only at this place? No, that is wrong. Left recursion is there even at the other level because S is AD. When you expand S with A, there is a left recursion even at other level. So if you straight away apply that formula, let us see whether the left recursion is completely eliminated. So if you apply the formula, what happens? There is no left recursion in the first production, so write as it is. Now here if you use the same formula, A to A alpha, beta 1, beta 2. So A to beta 1 A dash, beta 2 A dash or A dash to alpha A dash or epsilon. Straight away if you apply that formula, this is what you get as the equivalent. Look at this particular grammar, equivalent grammar. No doubt it is an equivalent grammar. What do we mean by equivalent grammar? Which defines the same language. So in this grammar, is the left recursion is completely eliminated? Look at this. Once again, when S is expanded by AA, so here what happens? A can be AA, D, A dash. You will get still, after elimination of the left recursion also, once again you will get left recursion. So remember that formula eliminates immediate left recursion but not left recursion at the other levels. It will eliminate left recursion only at the immediate level but not left recursion at the other levels. So if you really want to have a complete a grammar which is completely free of left recursion, that means there should not be left recursion even at the other level, means the criteria should be expand it first, then eliminate the left recursion. That is the best way. So if you really want to have a good solution for this, what you have to do is expand it first. A or B, A can be AC. Now expand this S first. What is S? S can be AAD or BD or epsilon. Simply I have expanded this S by AA or B. No doubt now there is a left recursion. Now apply that formula. So if you apply the formula, what we get? A can be A alpha 1, A alpha 2, alpha 1, alpha 2, beta 1, beta 2. So A2, beta 1 A dash, beta 2 A dash can be alpha 1 A dash, alpha 2 A dash or epsilon. Now look at this grammar. Now do you find any left recursion in this grammar? A is A dash. Now it is completely free of left recursion. So this is how you have to eliminate the left recursion if it is there at the other levels. Expand and then apply the formula. Now let us look at one more concept with the grammar, that is called left factoring. What is this? See, when you observe the context-free grammars, sometimes when you look at the right hand side of the grammar, sometimes you may find some common prefixes. Something like A2, alpha beta 1, alpha beta 2, alpha beta 3 and so on. There is a common prefix. Okay. So what is the problem with such common prefix? When every alternative contains some common prefix, what is the problem? Suppose when you have to derive any sentence out of such grammar, for example, if I have to derive alpha beta 3, parser initially looks at alpha. Looking at alpha, now it has to choose which alternative production to use for expanding A. You start with A, now you need to choose which string to be replaced. Since alpha is a common prefix, if you start with alpha beta 1, you will realize after seeing the next string, that is beta 3, that is not the right choice. Or if you go with alpha beta 2 also, by looking at the second string, you will realize later it is not a right choice. Okay. So whenever there is a common prefix, sometimes it may require a sort of backtracking for the parser, because it starts with alpha. Once it realizes like this is not the right choice, it may have to backtrack and should go with the next alternative. Remember, in computer science, backtracking is a very costly procedure. So if you really want to avoid backtracking, the best solution is left factor the grammar. Left factoring is nothing but taking out that common prefix. This is even called converting a non-deterministic grammar to deterministic grammar. Non-determinism means what? So many choices. Instead of having so many choices, now you convert into deterministic. So left factoring helps in converting non-deterministic grammar to deterministic grammar. So let us see how do we convert this non-deterministic grammar to deterministic grammar, or how do we left factor the given grammar. Process is very simple. Rewrite the grammar. While rewriting, take out that common prefix and whatever is left out in the remaining grammar, define that with some other non-terminal. So, I will take out the common prefix alpha here. To defining the remaining part, I will introduce a new non-terminal a dash, where this a dash stands for what? Whatever is left out in every alternative other than that alpha. That means it is beta 1, beta 2, beta 3. Do you find any commonality here in every alternative? No, everything is different. This is how you can left factor a given grammar. Advantage of left factoring is you can avoid backtracking. Let's take an example to understand this. The best example, the most popular example is Dangeling else problem. You know, if you take the syntax of a conditional statement if, sometime the tails will be Dangeling. So let us take that. Let's take an example of how to eliminate the left factoring. Best example is conditional statement. Conditional statement can be if expression then statement, if expression then statement, else statement, or in simple A, expression in simple can be B. So if you take some input string something like this is how we can verify whether what we get is a equivalent or not. So how do we left factor this grammar? How do we convert this non-deterministic grammar to deterministic grammar? What did I say? Take out the common part. Here the common part is what? IETS, and introduce a new non-terminal. Where this new non-terminal is what? It is whatever is left out. In the first part it is epsilon, in the second part it is ES, whereas S can be A. Add it here and E to B. So this is the equivalent. If you want to check out whether it is really an equivalent after left factoring, you can check out with this example. If you want to derive this string out of this, S is what? IET, yes, S dash, E can be B. So IBT I could get. Next once again S can be IET, yes, S dash. So IBT, A. S dash can be ES. So this can be A and S dash can be even epsilon. IBT, AEA. So that's how we can verify whether it is equivalent or not. So this is how you can actually given a grammar, if there are common prefixes, to eliminate the common prefixes, you can actually left factor the grammar. Advantage of left factoring is avoids backtracking. Advantage of elimination of left recursion is what? It avoids the parser going into infinite loop. Let's try to understand how to left factor the given grammar with an example. Let's take this example. Look at this example. Is there any common prefixes in this particular grammar? Yes. What is the common prefix? Yes, yes. So to left factor the grammar, what we have to do? Rewrite the grammar in such a way that take out that common prefix which is as, and to define the remaining part, introduce a new non-terminal S dash. So commonality is there between these two, so add the remaining as it is. Whereas this new non-terminal S dash is what? S dash is SBS here, and here left out is ASB. Now look at the resulting grammar. Do you still find any common prefix? Is it completely left factored? Similar to your left recursion. Sometimes when you perform left recursion, it may be still present. So do it at one more level. So still there is a left common prefix here. Once again left factor this grammar. So how do you left factor? Rewrite this as once again S2 AS double dash RB, where S double dash is what? SS dash, and here it is BB, where S dash is SBS or ASB. This is the left factored grammar. Look at this now, there is no common prefix, hence it is completely left factored. This is how you need to check out how many levels you have to left factor. Let's take another similar example here. Is to this one. So what is the common prefix here? The common prefix here is OSS, 0 SS. So take out that 0 SS
and introduce a new non-terminal S dash, whereas the remaining things has to be added as it is. Where this S dash is what? S dash is 1s here, whereas here 0s. And if you look at the resulting, once again there is a common prefix. So when there is a common prefix, once again left factor. So when you left factor this, once again what you get, S can be 0 S double dash R1, where S double dash is what? S dash R1. So this is your resulting grammar because S dash remains as it is. So this is your resulting.
Let's take this grammar and eliminate the left recursion. So here beta 1 A dash or beta 2 A dash, where A dash can be alpha A dash or beta A dash or epsilon. This is the grammar free of left recursion. Look at this. Now there is no left recursion here. Now let us do left factoring. How do we do the left factoring? Here the common prefix is AB. So I'll rewrite this as A equal to AB. Let me have some new non-terminal A, where this A is what? Left out here is AE dash. Left out part on the other side is BA E dash. This is my A. Now coming to E dash, if I left factor E dash, it is common part is B. So I'll introduce some new non-terminal and will add. So where B is what? Left out here is E dash, and in the other one it is E dash. This is the grammar what you get after elimination of left recursion as well as left factoring. Same formulas you can apply, and this is how you can check out. So today we have discussed some of the problems with the grammars which we need to know before the design of the parser. What to do if the grammar is ambiguous, how to check whether the grammar is ambiguous, and how to check whether the grammar is left recursive. If at all there is a left recursion, how to eliminate the left recursion, and how to left factor the grammar. These three are very important in the design of the parsers. So next we will discuss about how to design the syntax analyzer or the parser.